All right, so what will be an abbreviated day? The last thing I talked about was we're using direct methods, like Gaussian elimination and similar methods with pivoting, and how we're concerned about preserving sparsity, avoiding fill-in, and that's where we had this helpful MATLAB functions that could find good ways to interchange rows and columns to reduce fill-in. But now I want to talk about another aspect of solving systems linear equations, and really this applies not just for direct methods, but any of the methods that I'll be talking about. One thing we'll bring back from any numerical linear algebra course that you've had, well, you've all taken 610 at one time or another. The condition number of matrix A is denoted by kappa of A, and that is the norm of A times the norm of A inverse. And you cannot combine those to say that's the norm of identity. And you can use whatever norm you choose, whether it's the infinity norm or 2 norm. Okay, let's try that again. But the larger the condition number is, the more sensitive the system AX equals B is to round off error or any perturbation. So we don't like to have large condition numbers. But if A comes from a discretization of a PDE, generally speaking, it is still conditioned. Also, to make matters worse, the smaller your spacing, like your delta x or your h or whatever you call your measure of your grid spacing, that leads to an even larger condition number. So high resolution leads to badly conditioned systems of equations, which is actually one of the nice selling points of KSS to try to get around that for time-dependent problems anyway. Okay, so how can we deal with this? Can we need to try to find a way to get around the fact that such systems ill conditioned. So what we try to do is preconditioning. Okay. So the idea is there's two kinds: left preconditioning and right preconditioning. So in left preconditioning, all you do is you just multiply. So you solve the equivalent system where you just multiply both sides by some matrix P inverse. And P is called the preconditioner. And we'll talk about how we can select P in a little bit. So the idea is hopefully the matrix P inverse times A has a smaller condition number than A does. Right conditioning is similar. You have a preconditioner on the right. So A P inverse Y is equal to B. And then this is supposed to be X. So you solve this system first. So hopefully the condition number of AP inverse is less than the condition number of A. And then you solve PX is equal to Y. Because that would mean that X is P inverse Y. It might be reminiscent of like the whole process of using Gaussian elimination and with forward and back substitution. Yeah, it's kind of like that. Okay, so I can give an example of how well preconditioning can work. So just with a simple 2 by 2 matrix. So even a small matrix can be very badly conditioned. So the condition number of this matrix in the 2 norm. So this matrix is symmetric. So in fact, I can give a formula for the condition number. It is the absolute value of the smallest eigenvalue of A divided by the absolute value of the largest. More generally, the 2 norm condition number is the largest singular value divided by the smallest singular value. If a matrix is symmetric and positive definite, which actually this matrix is, okay. If a matrix is symmetric positive definite, the eigenvalues are the singular values. If a matrix is symmetric but not positive definite, then the absolute values of the eigenvalues are the singular values. So if you go ahead and compute this, like in MATLAB using the cond function, then you get roughly 1001. So it's not horrible, but it's not great either. So I would like to try to reduce that somehow. So, so one thing you can do is choose as a preconditioner just a diagonal of A. And one reason this is a good choice, trivial to invert a diagonal matrix. So then P inverse A would be 1, 1, and then 1 over 1,000. Okay, I'll try it as a decimal, 0.001 and 1. And it turns out that the condition number in the 2 norm of this matrix is only about 2.62. So, so in this case, it really helped. If you're not really sure what to do for a preconditioner, and preconditioning is a very active field of research in numerical linear algebra. Okay, preconditioning is a very active field of research in numerical linear algebra. People try to find preconditioners that work well for certain types of problems. Often problems that are related to PDE. Because if you know something about the matrix, like its structure, you might be able to find something that will work well, at least for those categories of problems. But one very simple preconditioner you can try is just basically diagonal scaling. Like you could try scaling a matrix on the, like you're multiplying on the left by a diagonal matrix like this one, then maybe like you want to make all the diagonal entries the same, or maybe make all the make all the row sums the same. There's one technique I actually covered in 610 called equilibration. You multiply by a diagonal matrix on the left to make the row sums the same. Then you multiply by another diagonal matrix on the right to make the column sums the same. And you can actually go back and forth and have it converge so that all the row and column sums are the same. And that can have the effect of reducing the condition number. But preconditioning is not easy, unfortunately. Okay, so in fact, I can give you an idea as to why it's a difficult problem, because the criteria that you want to meet, that you want to have your preconditioner meet, actually compete against each other. So There's two criteria. You want P inverse times A, or AP inverse, depending on whether you're doing left or right preconditioning, to be approximately identities. In other words, P should be approximately equal to A. But the symmetric, let's just choose P equal A. But then there's the other criterion. A system like Py equals B for generic Y and B, in other words, linear systems involving P, they need to be easy to solve. So, so you think about the extremes that would satisfy one of these criteria. So, if you want to satisfy this criteria and not care about the other one, you would choose P equal A. If you only care about this criterion and you don't care about the other one, then you would choose P equal to identity. You can't solve the system more easily than that. So the best preconditioner is somewhere in between. Now, in between is kind of difficult to define in a space of infinitely many matrices, but you get the idea. So for this reason, it's common to choose P to be diagonal. So that's definitely easy to invert. Or triangular. Or if A is already sparse, you want to have more sparse, because that's actually a good guideline in general. Something that's more sparse than A. So systems involving P must be easier to solve than systems involving A. Okay. Now, so to give some specific examples of preconditioners, if I divide A into parts, and this will be familiar to you from discussion of iterative methods. So the main diagonal, that would be D. The strictly lower triangular part would be L. And then the strictly upper triangular part would be U. So I could break down A into D plus L plus U. So I can use this notation to describe certain preconditioners. So here's some options for preconditioners. For instance, P is equal to D, just the diagonal part. This is especially a good idea if A is diagonally dominant, meaning the largest entries not only are the largest entries on a diagonal, but in fact the diagonal entries are larger than the whole rest of each row. So if you sum up the absolute values of the entries on a row, the diagonal entries, like the off-diagonal entries, the diagonal entry is still larger than that. And this is actually what leads to a well-known iterative method called the Jacobi method. I know I'm talking about direct methods, but I'm about to segue into iterative methods. Another option that's not quite as easy, but still pretty easy to work with for solving, like D plus L, which sets the stage for Gauss-Seidel. Okay. Because that is lower triangular. You can just solve a lower triangular system using forward substitution. Okay. Another possibility is incomplete LU factorization. So, also known as ILU. And there are many variations of ILU. So the idea is A is approximately factored into, we'll call them L tilde and U tilde. So it's not the true LU factorization. That would be too expensive. But like for instance, if A is sparse, you require these approximate LU factors to be sparse, even if the true LU factors perhaps might not be. Like for instance, what you might do is require that entries below a certain size are just set to 0. So you're just looking for some sort of approximation. Okay. And the way, so then what you can do, if you have this factorization, is you can do like both left and right preconditioning. So like P1 inverse A, P2 inverse Y is equal to P1 inverse B, where P1 is equal to L tilde and P2 is equal to U tilde, because that way by L tilde and U tilde approximating the true L and U, P inverse A, P1 inverse A, P2 inverse would be approximately identity, because what's happening is if A is equal to LU, like the exact LU factors, L tilde would approximately cancel out L, and U tilde would approximately cancel out U. So that's one way. Another way, there are different criteria for how to do this incomplete LU factorization, but it's a widely used preconditioning method. If A is symmetric, positive, definite, then you would do incomplete Cholesky, which works in a similar manner. So in MATLAB, there's a function LU inc, and also CHOL inc, Chol inc for incomplete Cholesky. So those functions can help you with the preconditioning process. So the trouble is, if A is ill-conditioned, it doesn't matter what method you're using to solve it, whether it's direct or iterative, conjugate gradient or multigrid, you're going to have a hard time. Ill-conditioning means the problem itself is bad. It's not really commentary on the method, compose problems for all methods. So really what you're trying to do is change the problem. And that's what preconditioning is meant to do. Any questions about these types of preconditioners? Okay. And preconditioning is often discussed in association with iterative methods, but really it can be used to help with any methods, direct or iterative. Okay, so now I'm going to take a look at stationary iterative methods. I just realized I have to digress for just a moment. I meant to bring this up earlier because this came out yesterday. For the homework, I goofed in the notes. So I fixed the notes, but now I need to fix what advice to give for the homework problem. This is problem 4B. So using Chebyshev points. So using Chebyshev differentiation matrix. So the system to solve is expressed in notes as a dn squared u is equal to f. But I need to be more careful about how I define this matrix. So dn is Chebyshev differentiation matrix for partial with respect to x, first derivative. And then dn squared is a full Chebyshev differentiation matrix for second partial derivative with respect to x. So you just go ahead and form dn using the formulas in the notes. But you have to include the boundary entries also, not just the interior ones. Then go ahead and square it. So dn tilde squared is dn squared with the first and last rows and columns removed. So in other words, the way it's described before was incorrect. Before I was saying was, take dn, strip out the first and last rows and columns, then square it. No. You square the full dn first, then strip out the first and last rows and columns. So what that means is, even though it's written this way, like in the notes, it's kind of misleading. That is not the actual, it's not the square of any particular matrix. So you can almost think of it as dn squared, and then this, you think of a tilde operation as removing first and last rows and columns. That would be a more accurate description. Okay, so because this is something I was looking at with someone's code where dn, the interior part of dn was formed correctly, then that was squared. That doesn't produce a correct solution. Okay, so had to clean up that mess from the second homework. Okay. Alrighty. Now, so stationary iterative methods. Start with ax equals b. I'm going to rewrite it into equivalence form. So that would be the same as 0 is equal to minus ax plus b. And then I'm going to add x to both sides. So then I have x is equal to x minus ax plus b. And then on the right side, I'm going to factor out an x wherever I can. So that would be identity minus ax plus b. So since your exact solution x satisfies this equation also, we can set up a fixed point iteration based on this equation. So xk plus 1 is equal to identity minus a xk plus b, where your first initial guess is some vector if you're choosing. Like if you don't know what to choose, you can always choose 0. But if you might have some approximate solution, if you do, then you should use that as your initial guess. Okay. Now, we don't yet know if this is actually going to converge. Well, in fact, well, I'll get to later what I determine convergence. This will not converge for general A. Basically, the eigenvalues of A have to be sufficiently close to 1 in order to have convergence. But we're not going to really stick this iteration anyway. We're going to mess with it to try to get something that we could be certain will converge, because we want to have something that converges for as wide a variety of matrices as possible. So what I'm going to do is I'm going to apply this iteration not to ax equals b, but to a right preconditioned system. AP inverse y is equal to B. So, so now my solution I can refer to as y. And then instead of the matrix A for my original system, I have this matrix for my modified system. So it's identity minus AP inverse YK. And then the right-hand side is the same. So I'll put that in there. Okay. But we're still trying to solve Ax equals B. That's our primary goal. And we have this relationship between x and y. Px is equal to y. So wherever we see y, I'm going to replace it with px. So px k plus 1 is equal to identity minus AP inverse pxk plus b. And then I want to simplify. So now I have p xk plus 1, and then I distribute the p through identity minus AP inverse. Well, this p is going to cancel with a p inverse over here, and then we'll end up with a p over here. So we're going to have p minus a. Okay, so now I have this relationship. I should mention, if you recall from seeing iterative methods in 610, we always had a splitting. A is equal to m minus n, and we discussed teaching iterative methods that way. So really, P is playing the role of m, and then this would be n. But I want to reinforce that the role of P in this case, which we referred to as m before, like in 610 or most books in iterative methods, it's playing the role of a preconditioner. Okay, so now I'm going to rearrange that. I want to get all the x's on one side. So now I have p xk plus 1 minus xk is equal to, and everything else that's left is b minus axk. Now, xk plus 1 minus xk, I refer to that vector as dk. D for direction. It's because it's the step you're taking to get from one iterate to the next. So it's how much your iterates are changing. Preferably the dk is going to 0. Now, this vector, b minus axk, we have a term for that. What do we call that from 610 land?
What is BAX minus B minus AX?
Yeah, what's the term for that? That's residual, yeah. So RK. So this is how your residual is related to the step you take from one iterate to the next. They're related by your preconditioner. So let's see. Residual, and this is DK. All right. All right. So here's what we could do as far as the process that we carry out for each iteration. So first, we have an x to start with, like it could be our initial guess, or whatever iterate we most recently have. So first we compute the residual. So set r equal to b minus ax, where x is your latest iterate. Now here I'm not using subscripts because typically in code you would not need them. You just overwrite everything as you go from one iteration to the next. So you compute your residual, and then you solve your preconditioned system. So PD is equal to R with that residual on the right-hand side, and then you update your solution based on that. So x is replaced with x plus O. Mistake in the notes is x plus D. For some reason, I have x equals x plus R. Okay. So once a preconditioner is chosen, we can just keep doing this. And once we have an initial guess, which could always be 0. So we just keep solving these preconditioned systems, keep updating our solution, until the residual is so small, or until D is so small, that we might as well stop. Because at that point, our iteratives have essentially converged. Okay. So any such iterative method can be described using this framework, and now we see why systems involving P have to be easy to solve. So we've established the need for that criterion, but now we need to check, when does this converge? Under what conditions on P or A does this converge? Actually, I'm going to leave this first part up here. When does this iteration converge? So for that, I'm going to define the error to be the exact solution minus our iterate. Because naturally, we want this error to go to 0. Okay. So I want to describe how the error changes from one iteration to the next. So I'll start with ek plus 1. And I want to get a relationship between ek plus 1 and ek. That I can see, okay, here's when it'll go to 0 or not. So now I'll take my formula for xk plus 1 from over here, and just, well, for people who are watching, this formula, I can solve this for xk plus 1. So xk plus 1 would be P inverse times everything on the right side, and I'll just substitute that in to what I have going over here. So that would be x minus P inverse times everything on the right-hand side. P minus A xk plus what on earth? Okay, this is a problem because over there I clearly have plus, and for some reason here I have a minus. I need to make sure that there isn't some other mistake. Okay, it's fine. It's the two wrongs make a right deal. So, yes. So I need to fix the notes. That should be a plus. Okay. So now you can just distribute this P inverse through everything. So now I'm going to have P inverse P that's identity minus P inverse A xk, and then minus P inverse B. But B is equal to AX, where X is the exact solution, so I'm going to fill that in here. Just as a side comment, it's interesting how P inverse was introduced into this in the first place as a right preconditioner. On the previous board, we're solving a right precondition system, but now we have P inverse multiplying A in the left. So that's kind of screwy. Okay, so now I want to simplify this as much as I can, because first I have, if I distribute, I have X minus identity times xk, and then I have minus, I'm going to go with this term first, P inverse AX minus plus P inverse AXK. Now, X minus xk, that's ek. And then in these terms, I'm going to factor out P inverse A, and what I'll get is X minus xk. But that's ek again. So I have ek minus P inverse A ek. So now if I factor ek out to the right, I finally get my expression for new error in terms of previous error. Ek plus 1 is identity minus P inverse A ek. All right, so this is how they relate. Okay, so we want to make sure that multiplying the error by this matrix, identity minus P inverse A, is causing the error to get smaller and smaller. So what can be shown is this iteration converges if and only if the spectral radius of identity minus P inverse A is strictly less than 1. No, that's just row, not row inverse. Okay, so spectral radius of this matrix has to be less than 1. Spectral radius is, from 610, that is the maximum of all the eigenvalues, maximum absolute value of identity minus P inverse A. Okay. So in other words, the eigenvalues of P inverse A ought to be as close to 1 as possible. So in other words, if you have like a disk in the complex plane centered at 1, and there's a disk around that of radius 1, all the eigenvalues of P inverse A in the complex plane must fall within that disk. So you have a situation like this. This is your complex plane. Here's 1. So all the eigenvalues of P identity, all the eigenvalues of P inverse A must fall within here. Okay. And now you can see from this why P should be a good approximation of A. Because then P inverse A would be a good approximation of identity. So identity minus that would have small eigenvalues, hopefully close to 0. Okay. So so we've seen from here why P should be equal to A. From before, we can see why P should be close to identity. But we can't have both. So we have to find some acceptable in between. Alrighty. So, any questions about these manipulations here? So now certain specific preconditioners. Well, I brought this up earlier, but now I can say more about it. Interrupted again. Because the infinity norm is the it's the maximum row sum. You sum the absolute values of all the entries in each row. You take the largest one. That's the matrix infinity norm. So since D is diagonal, you can easily write down what the inverse is, and what you end up getting is you actually write down what identity minus really D inverse A is. So if I write this as D inverse D minus A, that's the same as minus D inverse L plus U, because D is equal to A is equal to D plus L plus U. So what you have is you have the whole off-diagonal part of A divided by all the diagonal entries, and then negated. So it's a matrix that looks like this. You have minus, well, the diagonal entries are 0, and then you have A12 over A11, A13 over A11, A1n over A11. And then the next row you have A21 over A22, A23 over A22, and so on. And because the diagonal entries are larger than the sum of the absolute values of all the off-diagonal entries in that row, you can show that all of these row sums, because of this, have to be strictly less than 1. So this diagonal dominant, the row sums are less than 1, the infinity norm is less than 1, therefore the spectral radius is less than 1, and you have a convergent iteration. Okay. So that's one choice. Another choice, as I mentioned earlier, P is equal to D plus L. That is the Gauss-Seidel method. This is really a special case, so I'll just really talk about a more general case. D plus omega L, that's SOR, where omega is a relaxation parameter between strictly between 0 and 2. So when omega is equal to 1, that is Gauss-Seidel. And this is guaranteed to converge for any symmetric positive definite matrix A. Regardless of for any omega within that range, so that means that Gauss-Seidel will converge for any symmetric positive definite matrix also. In 610, one of the homeworks, you saw a variation of SOR, SSOR, that had a much more complicated iteration matrix, so designed for symmetric system. So Gauss-Seidel is like a variation of Jacobi that uses more up-to-date information about the solution than Jacobi does. So Gauss-Seidel, generally but not always, faster, more rapidly convergent than Jacobi is, but SOR, as shown in an example in 610, can be even much more rapidly convergent than even Gauss-Seidel. In some cases, there are formulas to choose the optimal omega, that makes the spectral radius of identity minus P inverse A as small as possible. Certain matrices that come from finite differences and so forth, but it's not always easy to find the right one. Okay. So questions about these types of iterative methods. All right. Okay. Funny thing is, like, the very next thing coming up in the notes is multi-grid methods, and if I think I covered those in the day when Haley's not here, she'll probably hurt me. So, well, at this point, does anyone have any questions about anything, or is this sort of homework or anything like that? Okay. Let's see. I think what I will do is, since the very next thing after multigrid does not depend directly on multigrid, I will cover that. Okay. So these are preload subspace methods. Not KSS, just KS, I guess. So a different sort of iterative method. So suppose the matrix A is already preconditioned. In other words, P is equal to identity. Then what that means is the iteration that we've seen before, as I was talking about, takes a very simple form. Xk plus 1 is equal to xk plus rk. Check my notation from the previous notes here. Oh, okay. For some reason in the notes, I switched from using this kind of superscript for rk to just using a subscript. Maybe the MIT notes are the same. But I'll stick with this. Okay, because what we had here before was not rk, it was dk. But dk is a solution of a system involving rk as a right side. If p is equal to identity, rk equals dk. So that's why I can say that. So if I write down what the iterates are from the beginning, so rk is equal to b minus a xk. So let's suppose I choose my initial guess to be 0. Therefore, my first residual, R0, would be b minus a times 0, so it would just be b. So then x1 is x0 plus r0, but that's 0 plus b, so we just get b. now I need the next residual. So R1 is equal to B minus AB. And now I can update the solution with that. So x2 is equal to x1, which is B, plus residual, which is B minus AB. So we get 2B minus AB. And then I compute the residual again. So R2 is B minus A times this. So 2AB plus A squared B. And then I'll compute one more. So x3 is equal to x2 plus residual. So if I put that all together, I have 3b minus 3ab plus a squared b. So if you look at what form the solution has, here we have a linear, we had just b. Second time around we have linear combination of b and ab. Third time around, linear combination of b, ab, and a squared b, and so on. So what we could say is xk belongs to the span of b, ab, a squared b, and so on, all the way up to a to the k minus 1 b. So a vector space of this form, so a subspace of Rn, is a Krylov subspace. It's Krylov, not Krylov, as I learned after many years of pronouncing it wrong. Okay. Before we move on, besides that pattern, as the most important to us, what kind of vectors made up each iterate. Anyone see what the pattern is in the coefficients of the x's? It is Pascal's triangle, or like all of it except this one boundary is stripped away. Yeah, because you get the coefficients like 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. But alternating the sign and one coefficient is missing. Okay. Now, the thing is, this particular choice of iteration, where we just add on residual every time, might not produce the best results. First of all, it's only going to converge if the eigenvalues of A are close to 1, and that's why we're assuming that A is already preconditioned, that A should already be a pretty decent approximation of identity. So more generally, whether A is already preconditioned or not, there's a whole family of methods that try to solve solve A equals B using a Krylov subspace. So we try to find some vector within that Krylov subspace, so that you can think of it as generating a polynomial of A times B. And there are different ways of finding that polynomial that is best in some sense. Okay, so what all Krylov subspace methods have in common is that your iterate xk is equal to some initial guess, like often we just say initial guess is 0, but in case it's not, I have to throw this term in there. Initial guess plus some polynomial of degree k of a. I need to check my notation. Okay, so for this next one, okay. Actually, degree k minus 1. So polynomial a times b. And so you keep updating its polynomial, increasing its degree from iteration to iteration, in the hope that this will eventually give you an approximation of a inverse times b. Now, so the only should say significant operation, or an operation of significant expense is just matrix vector products. Like computing products that form y is equal to a times x for some vector x. So you can think of this could be some black box operation. You don't even need to have a in the usual form, like as an array of entries, not even a sparse matrix. If you just have some function whose job is to take a vector in, multiplied by a, and spit the result out, that would be enough for a Krylov subspace method. So other methods, direct methods, stationary iterative methods, do not have that kind of flexibility. You need, for most methods, you need the actual entries of a. So here you don't. Okay. So some examples of Krylov subspace methods and the criteria that are used. So first, I need to introduce some notation that I should have introduced earlier. So big K sub little k is this Krylov subspace. So that's the span of B, A, B, A to K minus 1, B. So the subscript here is the dimension of the Krylov subspace. So what the different Krylov subspace methods do, so one option is to have the residual RK be orthogonal to the Krylov subspace. So in other words, you want to have all residuals orthogonal to each other. And this is the idea behind conjugate gradient. And actually, if you enforce this criteria, you actually get the Lanczos algorithm, but then improving the efficiency of Lanczos leads to conjugate gradient, as I derived exhaustively in 610 over a span of 3 class periods. An alternative criteria is you want to choose an approximation within this Krylov subspace so that the 2 norm of the residual is minimized. And that leads to the method called minres for symmetric matrices, or GMres if a matrix is not symmetric. So minres is minimum residual. GMres is generalized minimum residual. So GMres is probably the most often used iterative method for general systems where you don't have any particular nice properties of A. It's maybe not the fastest method, but it's certainly quite reliable. MinRes also uses the Lanczos iteration. It differs from CG, from conjugate gradient, in that how it computes each new iterate from a Krylov subspace is a little different. It's actually solving a least squares problem. GMRes does the same thing using Arnoldi iteration, which is a generalization of Lanczos to non-symmetric matrices. A third criteria, another effort to generalize conjugate gradient to more general matrices, is to have the residual orthogonal not to the Krylov subspace based on A, but a Krylov subspace involving A transpose. And this leads to bi-CG, bi-conjugate gradients. So that uses the unsymmetric Lanczos algorithm. So you can think of GMRes and bi-CG as different ways of generalizing CG to general matrices. From regular Lanczos for symmetric matrices, you can go to unsymmetric Lanczos, which still leaves you a tridiagonal matrix, or you can go to Arnoldi, which produces a Hessenberg matrix rather than a tridiagonal. But the thing is, unsymmetric Lanczos is unstable. So they fixed bi-CG, and that leads to what's called bi-CG staff. So there are functions for these iterative methods in MATLAB that are named after the iterative methods. Well, CG, it's called PCG, is a function for conjugate gradient. The P stands for preconditioning, because conjugate gradient is best used with some sort of preconditioning. But yeah, there's functions for GMRes, there's a bi-CG function, there's a MinRes function. So all of those are available in MATLAB. You can look at the help pages, see how to use them. For homework 3, we'll take a look at using PCG as a way to compare against a multi-grid approach. Okay. And one more is try to minimize the norm of the error from one iteration to the next. And that is the general idea behind SymLQ. So that's another iterative method for symmetric matrices. It's especially useful if a matrix is symmetric but indefinite, having both positive and negative eigenvalues. Because if they're all one sign, you can use CG. But if that's not an option, then SymLQ is a good idea. Oh, look at that rain. Dang. Okay.